So today we're going to be talking about step functions. Various piecewise continuous functions, the Laplace transform, how it relates to them, shifting functions backwards and forwards on the t-axis, and how that affects the Laplace transform, and finally shifting functions backwards and forwards, shifting the Laplace transform backward and forward, and seeing how that affects the inverse Laplace transform. Okay. I'm actually going to turn this light on. Okay. So, like I said, today we're talking about step functions. And so the simplest example that I can give of a step function is called the unit step function, also known as the Heaviside function. This is named after a mathematician whose last name was Heaviside, and his first name I don't remember. But he did a lot of work on advancing the understanding of Laplace transform. Okay, so this function has a parameter c. So we write it like this: the function of t, and this is a function that is 0 whenever t is less than c, and it's 1 when t is greater than c. Now draw a picture of this. So let's say this is 1 right here on the output axis. We'll call this axis UC, this axis T, and maybe right here is C. So the way this function looks is it is 0 all the way up to C, and then at C suddenly makes a jump up to 1, and then it stays at 1 forever. Okay. Now, you'll notice that I didn't specify what happens exactly at C, and that's because the value, this is a piecewise continuous function. You can see it's got two pieces and that both are continuous. The value of a piecewise continuous function at its discontinuities doesn't matter. For anything that we're doing, the actual value at those discontinuities doesn't matter. So we could arbitrarily say it's always 0, or it's always 1, or we can make it halfway between these 2 points. An interesting idea is to say the value of the function there, or we could just say we don't care because it doesn't matter. That's what I'm going to do. Okay, now we had this physical model for the things that we had been talking about so far. So the mechanical vibrations model, and we might think of this as this could be like a forcing function that we use. So there's no external force being applied to the mass that's moving. And then all of a sudden we will apply a continuous force. Maybe it's got a little rocket attached to it, and that rocket just continuously applies a certain amount of force to the object. Something I didn't talk about at the time of when we were talking about mechanical vibration that I probably should have was that there's also an analogy between that system of mechanical vibrations where we have the mass of the object, we have air resistance, we have a spring constant, and we have some external driving force. There's a direct relationship, or there's an analogy between a system like that and an electric circuit with capacitance, resistance, and inductance. And if we think of the mass as being analogous with inductance, with resistance being analogous with the air resistance constant, and the capacitance being analogous with the spring constant, then you get the exact same differential equation that will model this system, this electronic circuit. And then you have an external voltage being applied, and that corresponds to the driving force. So in that case, we can think of this. There's an even better analogy because it was kind of hard for me to come up with a force that you apply suddenly to an object, but a voltage that you apply suddenly to an object to a circuit. That's really easy. That's just flipping a switch, right? So we can think of this as at this point we flip on the voltage of the circuit. So that's interesting. Now, one thing I kind of want to point out is that this is a discontinuous function. It's pretty close to being a continuous. There's only discontinuities, isolated points. But in the real world, we always make this assumption about the real world that all of the things that we measure about it they vary continuously, right? So this is sort of an abstraction of what we think happens in the real physical world, but it's very close to reality and close enough that it's useful. And also it has the advantage that the Laplace transform deals with it very. Another very simple example that I can show of using this kind of step function is I'll use it to model a system where initially the voltage is on and then we flip a switch to turn it off. So this was a picture of UC. C1. And now we want to model a situation where the voltage is off. Sorry, that's the one we had before. Where the voltage is on. And then suddenly it goes to zero. The force is initially a certain value and then it goes to zero. So this is modeling flipping off. I'll just flipping the switch off. And so, well, we can think of this going all the way back in time, all the way up to C. This is equal to 1. And then when we hit the time C, we're going to subtract away 1 from it. So we can think of that as 1 minus UC. So those are just a couple of very simple examples. So here's another one. Let's suppose we have this function and it has 2 terms. We have u pi of t, and then we're subtracting away u 2 pi of t, and we're only considering this function when t is positive or non-negative. So what does this look like? So if this is t, let's say we have 0, pi, 2 pi, 3 pi, and here is 1. What does this function look like? Or let's try to figure out what this is equal to. So we have a function that's defined to be 0 up to the point that it is up to the point t is equal to pi. So 0 when we're go from 0 up to pi, and then it's 1 for t greater than pi. I put less than or equal to pi. I should just put less than pi, because I don't care what it actually is. This off. This is not part of the equality. This is this equality. Okay, so we have that, and then we subtract away from it something that is 0 when t goes from 0 to 2 pi, and then it's 1 after 2 pi. So we have well, we really have two discontinuities. Okay, there's going to be a discontinuity here at pi and at 2 pi. So the function's going to change there. So we'll split it up into the 3 subintervals from here to here, here to here, and then from then on. Let's see what that looks like. So the first one is from 0 to pi, and then from pi to 2 pi, and then from 2 pi onward. Okay. So on this interval, both functions are 0, so we get 0 minus 0. On this interval, the first switch is turned on, but the second switch is still off. So I get 1 minus 0, which is just 1. And then once we hit 2 pi, the first switch is on, the second switch is on. We get 1 from the first one, get -1 from the second one, so we get 0. So it looks something like this. Let's what color it up? Blue. So it's going to be like this, and then 1 from 0 to 2 pi, and then it's going to be 0. So just a straightforward example. Let's move it up like this, and do another simple example. So we got a function that was written in terms of our unit step function, and then we rewrote it as a function, this piecewise function here. Now we can go in the other direction as well. Let's say we have a function ft, and this one is equal to 2 when go from 0 to 4, 5 whenever we go from 4 to 7, -1 whenever we go from 7 to 9, and it's 1 past 9. So I'm going to pause just for a second and give you a chance to kind of think about this. See if you can come up with a sum and a linear combination of unit step functions that give you the same thing as this function right here. Maybe I'll say really quickly, what's the point of it? The point is that if we can rewrite this in terms of unit step functions, we're eventually going to have a formula for the Laplace transform of unit step function. And so if we can do that kind of rewriting, we can apply that formula without much thought. We'll just give this a try really quickly. Okay, I'll go ahead and we'll see what I come up with. So I want this function to start off at 2. So going from 0 up to 4, it's equal to 2. That's easy. That's just 2. Now at 4, I'm going to transition from 2 to 5. So if I'm starting at 2, I want to go up by 3. I'm going to say plus 3 UC. My C is going to be what? It's going to be 4. Okay. So this will start me off at 2, and then when t is equal to 4, I'll jump up to 5. Now, when I get to 7, I want to drop down to -1. So if I'm at 5 right now and I want to go down to -1, sorry, I will go down by 6. This will be happening at t is equal to 7. So I get -6 times u7 of t. And then finally, I'm going to go from -1 up to 1. So I'll be adding 2 to that. And that will be happening at t is equal to 9. So I'll add a +2 u9 of t. And there's my function in terms of unit step functions. Okay, now that we've had a little bit of time to get comfortable with the unit step functions, let's look at the Laplace transform. The Laplace transform of uc of t, what is this equal to? Well, before I go on to computing what it actually is, let's figure out if it exists and for what values of s it exists. So uc of t, remember this is it's 0 for a while, and then it switches to 1. Now this thing is bounded by a constant, right? We can take all of its values and set them below a constant. In fact, we can set them below the constant 1. So this is always bounded by e the 0t, which is 1. So this is definitely of exponential order, and the growth rate of that exponential is 0. So we know for sure that this exists, and that it exists for s greater than 0. So what do we get? Well, we'll have the integral from 0 to infinity, e to the minus st, u sub c of t, dt. And so this u sub c of t is 0 for a while, up until we get to the point C. So we can just get rid of that part from 0 to C and just take the integral from C to infinity of e to the minus st, because from this point on, uc is 1 dt. And now this is easy to compute the antiderivative of. This will be negative 1 over s e to the minus st, evaluated at c and infinity. Or I'm doing this kind of lazy thing where I'm not writing out the limits. Really, I want to know what e to the minus s a is as a goes towards infinity. But really, if we know s is greater than 0, which we do already know because that's where we're saying the thing exists, then as t increases, we have an exponential decay. So this thing goes towards 0 at infinity. So it's 0 minus what I get when I plug in c, which is negative 1 over s. So it's positive 1 over s e to the minus c s, right? Which is just e to the minus cs over s. So now we have the Laplace transform of the unit step function. And we know it's defined in the really s greater than 0 is the widest s-plane, that we consider. So really, we this is as good as it gets. Okay, so one thing to note is that what if we look at u0 of t? Well, if we plug in 0 for c, we just get 1 in the numerator, and so we get 1 over s. And if we think about what u0 of t is, if we're only considering whenever s is greater than 0, I'm sorry, we're only looking at the situation when t is greater than 0, right, in this integral, then this is just the same thing as the Laplace transform of 1. And we've previously seen that that is the case, that the Laplace transform of 1 is 1 over s. An interesting thing to note that it works out with, sits in the bigger context of what we've looked at before. Now, let's say that we have a function. Let's say we have we're starting to apply this thing. We have a continuous function f. And so we might think of this as being applied from time 0 forward. So maybe it looks something like this. This is a graph of the forcing function, for example, or a voltage that we're applying to the circuit. Starting from time t is equal to 0, going forward, we have some function applied. And let's say we want to take this exact same function and we want to shift it forward in time. So we're going to have this function where initially we're applying no force. So that's up to time. Oh, I thought maybe I could do this where I've done this accidentally many times, where I select a line that I've drawn and I can move it. But apparently when I try to do it on purpose, it doesn't work. Okay, so let's just try this. We're going to shift it. So let's shift it like this. So maybe we'll end up with something that kind of looks like this, right? So that's our function shifted forward by some amount c. So our new function is going to be equal to 0 up to that point, and then it's going to be equal to that original function, but shifted forward. Right? Now, if we could get the, let's say, if we have the Laplace transform, I'm just going to abbreviate, of f and can, combined can and we get the Laplace transform of G? And the answer, maybe surprisingly, maybe not surprising, is yes. Well, I probably wouldn't be asking the question if the answer was no. You're wasting your time. But how do we get that out of the integral? Well, let's gather this together as a theorem, and then we'll prove it. So if the Laplace transform of f of t, which we'll write as capital F of s, Laplace transform of f, exists for s greater than a, and if c is some positive constant, so that's the amount that we're shifting it to the right by, then the Laplace transform of, oh, let me take a step back. I was about to write that in step functions. We can write this thing in terms of step functions as well. We want to shift the function by f of t. Instead of writing it as these two pieces in the curly braces, I'm going to write it as a sum of things in terms of step functions. So it starts off for a while at 0, and then it switches on. So that's going to be the same thing, uc of t. And then I'm going to multiply that by the function shifted forward. So the function, maybe the function looks something like this going back in time, but we don't want that part before t is equal to 0. We want to start our forcing function at time c. So this turns it on at time c. This is the function itself shifted forward by c. And so the Laplace transform of this thing, the shifted function, does exist. And in fact, is equal to e to the minus cs times the Laplace transform of f. And of course, we can rewrite this just as e to the minus cs times f of s. And it exists in the same place that the other one did, which is s greater than a. And of course, the Laplace transform works in the other direction. So conversely, if f of t is the inverse Laplace transform of f of s. So if we knew how to work backwards from f of s, then we also know how to work backwards. Well, write this. In other words, what am I saying? I'm saying that f of t is equal to the inverse Laplace transform of capital F of s, Then we have the inverse Laplace transform of e to the minus cs f of s as well. And it is just what we expect. It's the shifted version of f, starting at t is equal to c. All right. Now, how do you get such a thing? How do you show that this is true? We have this interesting, before I go on, we have this interesting relationship. In the time domain, we have shifting back and forth in time. And in the complex frequency domain, we have shifting, we have multiplication by a particular exponential decay. So this e to the minus, yes. So it turns shifting into multiplication, and going back in the other direction, it turns multiplication by an exponential into shifting. Kind of an interesting property. Well, let's look at Laplace transform of uc of t, f of t minus c. Of course, by our formula for the Laplace transform, equal to the integral from 0 to infinity, e to the minus st, uc of t, f of t minus c, dt. Now I can basically just do a u sub at this point to solve this integral. So what I'll do is use green. This t minus c will be my u. So du is just the same thing as dt in that case. And t is equal to u plus c. So I can rewrite this thing as the integral. I'll return to the upper and lower bounds in just a second. E to the minus s times u plus c. F of u du. Now, of course, I have to change my upper and lower bounds. They were previously in terms of t. Now they're in terms of u. And so what I get, my notes don't match what I was expecting. Okay. Well, I guess I didn't write down this detail. But anyway, since this is in terms of u, the upper limit is going to be infinity minus c, which is just infinity. The lower limit is going to be u minus c. But remember that this function f was only defined for 0 forward. So we don't have any, it's 0 for negative c at 0. So we just rewrite this thing as integral from 0 to infinity of e to the minus, well, I think what I will do is I will write this as e to the minus s u, e to the minus s c, f of u du. No problem. And now this e to the minus c part I'm going to move that. Let's see if this works. Nope. I thought maybe I could select it. No, that's okay. What I'm going to do is I'm going to move that out. So instead of erasing it, writing it, it's just e to the minus c, the integral from 0 to infinity, e to the minus su, f of u, du, which is just e to the minus sc times the Laplace transform of f. And since we wrote it before as cs, we'll write it now as cs. Now, to get the converse of this, we just apply the inverse Laplace transform to both sides. Now, I'm going to let's do an example of this. All right, got a little bit to get through in my notes here. Let's try to do these examples quickly. So the first example of the function, which is sine of t goes from 0 to pi over 4, and sine of t plus cosine of t, but shifted forward by pi over 4. And so this is for t greater than pi over 4. Okay. Now let's try to find the Laplace transform of this. This is equal to starts off at sine of t. And then when we get to pi over 4, we add to it this cosine. So that's just the shifted version of cosine starting at pi over 4. So that's u pi over 4 of t cosine of t minus pi over 4. And now we have the Laplace transforms of each of these pieces. We have sine of t, and we have the Laplace transform of this in terms of the Laplace transform of cosine of t, which we talked about last time. I looked up in a table of transforms. So the Laplace transform of this whole thing is, we can use linearity to split it up. Laplace transform of sine plus, we have this formula for shifting. So we will get e to the minus pi over 4s Laplace transform of cosine of t, which we also had from last. The Laplace transform of sine is a over s squared plus a squared plus e to the minus pi over 4s times the Laplace transform of cosine, which is s over s squared plus a squared. And so that's our Laplace transform. Now maybe we can rewrite it as a single fraction. Let's skip that. Okay, another example. We're going to use this fact about the inverse of Laplace transforms. So let's say that we have this function. We've solved our Laplace transformed version of the differential equation, and we end up with this. And we want to get f of t. So the inverse Laplace transform of f, again, we have linearity. So we can split this up into two pieces. the inverse Laplace transform of 1 over s squared minus the inverse Laplace transform of e to the minus 2s. Write that in front. E to the minus 2s, 1 over s squared. Now, this inverse Laplace transform I'm looking up in a table as well. We didn't work this one out, but the inverse Laplace transform of 1 over s squared is just t. This will be just t. And we have this multiplication of an exponential out in front. This just corresponds to shifting. So this is again t, but we're going to shift it forward by 2, right? So this e to the minus cs, so our c is 2. So this is equal to t plus u2 of t times t minus 2, the forward shifted t. Now we can actually apply a shifting to the Laplace transform as well. So not just the original function, but the Laplace transform function as well. Okay, but we rushed through those two examples, so I think. So if we have that f of s is equal to the Laplace transform of f, and this exists for s greater than a, and if c is a constant, so that's how much we're shifting by, then the Laplace transform of e to the ct, f of t, is equal to of s minus c, for s greater than a plus c. So if we shift our Laplace transform function left to right, then that actually corresponds to multiplying our original function by an exponential. So going in the other direction, if ft is equal to the inverse Laplace transform of f of s, then we have e to the ct f of t is equal to the inverse Laplace transform of f of s minus c, so the shifted version of the Laplace transform. So that's interesting that the Laplace transform turns shifting into multiplication by an exponential in both directions. Now, how can we prove this? Well, if we just look at the Laplace transform of this, e to the ct f of t, integral from 0 to infinity, e to the minus st, e to the ct f of t dt, which is just the integral from 0 to infinity of e to the minus s minus c t f of t dt. Now, the only thing we've done here is we have the original Laplace transform, except the s is replaced with s minus c. So this is just the Laplace transform of f with s replaced with s minus c. Now, the only thing that we haven't touched on is this part, the restriction that this is defined whenever S is greater than A plus C. And the reason we have this restriction is if we had before that this Laplace transform exists for S greater than A, then we have that the absolute value of f of t is bounded by an exponential with growth rate A, eventually bounded by this exponential. So eventually, we go forward in time, will eventually be bounded by. Then just multiplying both sides by e to the ct f of t, we get that this is a plus c t, and so now our growth rate is a plus c. And so this function will be bounded by an exponential with growth rate a plus c. So we have it defined when s is greater. Now this is really useful because it allows us to get the inverse Laplace transform of a much wider range of functions. And this is an example. So let's suppose we've done something like we did yesterday. We took our ODE, we did the Laplace transform, we solved the algebraic equation in order to get the Laplace transform solution. And what we came up with, actually use the same notation, capital Y. Let's suppose that after that whole process, we got capital Y is 1 over s squared minus 4s plus 5. Right? Totally plausible thing to come up with at the end. We want to get the inverse Laplace transform so we can get our solution. Now, if we try to factor this thing and use partial fraction decomposition, we end up with some complex numbers. Maybe that's not so bad, but we can actually get around having to do that by using this shifting of the Laplace transform. So if we look at this, what we have is 1 over s minus 2 squared. S minus 2 squared is just looking at these two terms right here. We took s minus 2 squared, we would get s squared minus 4s, right? We get s squared minus 4s plus 4. So we get s squared minus 4s plus 4 plus an additional 1 here from this 5, right? Completing the square. Now, if we think of this, if we think of f of s as equal to 1 over s squared plus 1, which we know how to take the inverse Laplace transform of, then this thing right here is just that thing shifted. Right? It's just s replaced with s plus 2. Now, since we have the Laplace transform of f, the inverse Laplace transform of f, just sine of t, then what we get for the inverse Laplace transform of y, that's our solution. That would be the inverse Laplace transform of f of s minus 2, which our result that we just saw tells us that this is equal to e to the 2d times the Laplace transform, just f, which we know is e to the 2t. I think, well, we still got 7 minutes, ending a little early. One thing I do want to say is that if we broke this thing up into, well, let's take a look at that. So if we had, what are the roots of this polynomial? So it's negative b plus or minus b squared minus 4ac over 2a. That would be the roots of this thing. And so that's equal to 2 plus or minus the square root of negative 4 over 2, which is 1 plus or minus 2i. Right? So what we would get is 1 over s squared plus 4s plus 5 is equal to 1 over s plus, sorry, s minus 1 plus 2i, s minus 1 minus 2i, right? Which we could have split up using partial fraction decomposition. And we could have solved for a and b in terms of complex numbers. And we would have got something with an exponential where the constant here is ultimately what I'm getting to is that this is a complex number. So we use Euler's formula. When we did these kind of inverse Laplace transforms before for this, when we did that example yesterday, we got e to the something times t, where that something was a real number. So what we got is a linear combination of two exponentials. I think one of them was a growth and one of them a decay. But when we have a complex number, we end up with a sinusoidal component. We end up with an oscillation as well. And that's actually what we ended up seeing right here, was that we had not only an exponential growth part to our solution, but we had an oscillatory part to the solution as well. And so you see, if we go to those two different paths, we end up with the same solution, but I'm not going to those now because it's not an especially important problem for us to see. See, is there anything that we can do in the last 4 minutes? Maybe I'll just end there for today and say that I will be out of town on Monday and Tuesday. So if I can get internet, which I should be able to get internet, I'll be doing the class from Cleveland. And if I can't get internet, then what I'll do is I'll do a recorded lecture and have a video that you can just watch for those 1 or 2 of those days. But probably not. I'll probably, yeah. Okay. If there are any questions, I'm here. Otherwise, I'll see you tomorrow.